Picture this scenario. You build a machine learning pipeline from scratch, right?
Sounds like a good day so far.
Yeah, exactly. So you run your cross-validation to see how well the model learns.
Which, for those new to this, is just testing the model on different chunks of your data to make sure it's actually learning patterns.
Right. And the results come back at a perfect 98% accuracy.
Oh, wow. Time to celebrate.
You deploy it to production expecting a massive win. But then, within hours, the accuracy absolutely crashes to 62%.
Ouch. That's a bad day.
A terrible day. You spend days tearing your hair out, debugging every single line of logic, only to discover that it wasn't a math error or a logic bug at all.
No, it rarely is in these cases.
Your pipeline was silently modifying its own data across different steps. This is a massive system reliability failure caused by a phenomenon called uncontrolled mutation.
It creates what we call the perfect accuracy illusion. Like, the model appears world-class during testing, but the pipeline is secretly cannibalizing its own training data right behind the scenes.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
Glad to be here for this one. It's a huge topic.
Today, we are taking a basic Python concept, mutability, which is where objects share references and change in place, and showing you exactly how it scales up to completely break entire machine learning pipelines.
Yeah, mutability is often introduced early on as just, a quirky language behavior. But in data science and AI engineering, it dictates pipeline correctness, reproducibility, and system trust.
Because trust in the data pipeline is a prerequisite for trust in the model, right?
Exactly. If you can't trust the data, the model is useless.
So let's introduce a mock project. We'll call it OS Automator to demonstrate how this breakage happens. We are building a tiny pipeline.
Okay, let's hear it.
Step 1, you load some data. You have a list of file sizes. Say file A is 10 megabytes and file B is 20 megabytes.
So the original raw data is sitting in the system's memory, just ready to be processed.
Right. Step 2 is preprocessing. We write a function that loops through that data and multiplies the file size by 2, for scaling purposes.
Makes sense.
We run the function, and we save the output to a new variable called processed. So now we have a data variable and a processed variable.
Two separate variables.
Exactly. We print them both. But the trap springs. Both have changed. The original data no longer says 10 and 20. It says 20 and 40.
Yep. The intention was to process a copy, but the original source was completely overwritten.
Now wait, I have to ask a beginner question here. If my end goal is just to process the data to feed it into a model, why wouldn't I want to save memory and just change it in place?
It's a fair point.
Like if I have a massive data set, overwriting the old data seems like, I don't know, the most efficient route. What's the harm?
Well, efficiency is important, definitely. But what happens here is something called side effect mutation.
Okay, what does that mean?
So in many languages, like C++, a variable is like a bucket. You put data in the bucket. If you create a new variable, you get a brand new bucket.
Right, physical separation.
Exactly. But in Python, variables are not buckets. They are sticky notes.
Sticky notes, I like that.
Yeah. When you assign that preprocessed output to a new variable, Python didn't create new data. It just took a second sticky note called processed and slapped it onto the exact same object in memory that the original data sticky note was attached to.
So the two variables are just different road signs pointing to the exact same house.
Yes, perfectly said. And when the function mutates the house, like when it remodels the kitchen in place, the original state of the house is just lost forever.
So why is losing the original state so disastrous for machine learning?
Well, in a machine learning pipeline, losing the original state destroys your ability to audit the data.
Well, like tracing errors.
Exactly. If a model spits out a bizarre prediction in production, an engineer needs to trace that error back to the raw input to understand what went wrong.
But if the raw input was overwritten,
then that trace disappears entirely. The diagnostic trail is just severed. You have no idea what the model actually saw.
wow. And this points us directly to a really foundational concept in reliable system design, which is idempotency.
Idempotency, yes. It's a big word, but it's a simple idea.
Right. Mathematically, it's defined as f of x equals f of x.
Which basically means running a function once or running it 1,000 times must yield the exact same result as running it that very first time.
The sources had a great analogy for this. Think of non-idempotent code, like adding salt to a pot of soup.
Oh, I love this one.
Yeah, you taste the soup and it needs salt. You add a pinch, that's your first function call, and this soup is perfect.
Delicious.
But if you accidentally run that function again and add a second pinch of salt, the meal is ruined. The state has been irreparably altered by that second application.
Right. You can't unsalt the soup. Translating that back to the OS Automator example, if the pre-processing step that multiplies the file size by 2 accidentally runs 3 times, the file size goes from 10 to 20, then to 40, then to 80.
And in the real world, pipelines restart all the time, right?
Oh, constantly. A network connection drops or a task orchestrator like Apache Airflow just retries a failed job.
So if the pipeline restarts and runs the pre-processing step again on data that was already mutated, the machine learning model receives absolute garbage.
Exactly. The statistical distributions shift entirely. A feature that was supposed to represent a normal file size now represents a massive anomaly.
And the gradient descent algorithm, which is, the math trying to optimize the model and find the lowest error, it goes completely haywire because the underlying landscape is just shifting beneath its feet.
It's trying to hit moving target. Let's elevate the stakes here to a healthcare safety example from our sources just to show this isn't just theory.
Okay, let's do it.
Say you are building a medical AI. You have an array of raw lab results from a patient. Let's say it's blood pressure readings.
Okay.
You got 95, 110, and 105.
So the model requires normalized data to process it. By normalized, we mean scaling the numbers down so the neural network can handle them easier.
Right. So you write a normalization function that loops through those results and divides them by 100 in place.
So the array becomes 0.95, 1.10, and 1.05. The model trains successfully, but the raw data in the system's memory has been permanently altered.
Yep. And here is the terrifying real-world consequence. A doctor logs into the system later to review the patient's original lab results to make a treatment decision.
They expect to see 95 and 110.
Exactly. But they are presented with 0.95 and 1.10 because the pipeline mutated the underlying object.
Wow. The doctor might interpret those dramatically low numbers as a critical health failure, leading directly to a misdiagnosis.
Yeah, mutation in this context is not just a coding bug. It's a safety-critical issue that impacts human lives.
So how do we fix this? How do we prevent the mutation?
To prevent this, we have to isolate the transformation using defensive copying. Python actually provides a copy module for this.
But we need to use copy.deepCopy, right? Passing the data in, not just a standard shallow copy.
That is a crucial distinction. A shallow copy only creates a new outer container.
Like a new folder, but the files inside are the same.
Exactly. If you have a patient record containing a nested list of past hospital visits, a shallow copy creates a new patient record, sure. But the list of visits inside still points to the original memory references.
So if you mutate a past visit in the copy, it still mutates the original patient's history.
Yes. Deep copy solves this by recursively traversing the entire object and creating brand new independent clones of absolutely everything it finds, no matter how deeply nested it is.
So the original input remains perfectly untouched.
Yes.
Okay, I need to push back here, though, because deep copying everything sounds great for safety, but what about infrastructure limits?
Oh, the memory problem.
Yeah. If I'm working as a data scientist, spinning up an AWS EC2 server, and I have a 10 gigabyte data set, deep copying means I suddenly need 20 gigabytes of RAM.
At a minimum, yeah.
And if I have multiple pre-processing steps, I might need 30 or 40 gigabytes. I will definitely hit an out-of-memory error, the server will crash, and the pipeline fails anyway.
And that right there is the ultimate engineering trade-off. Memory safety versus memory capacity. Deep copying massive data sets indiscriminately is just not viable in production.
So what's the solution then?
The solution is adopting an immutable architecture where possible, or explicitly managing garbage collection.
Meaning you clean up after yourself.
Right. You process a chunk of data, create the new transformed object, and then deliberately delete the old object from memory using Python's del keyword to free up the RAM.
Ah, so you maintain idempotency without permanently doubling your memory footprint.
Exactly.
That makes a lot of sense.
Yeah.
You have to manage the memory explicitly rather than letting mutations happen silently, because silent mutations often come from hidden traps in Python itself.
Oh, there's so many traps.
Let's talk about trap number 1, mutable default arguments.
This is a classic beginner mistake.
You write a function like def additum, and it takes an item and a container that defaults to an empty list. So container equals empty brackets.
Seems totally innocent.
Right. You call the function and pass in the number 1. The output is a list with 1 in it.
Perfect.
Later, you call the function again in a completely different part of the code, passing in the number 2. You expect a fresh list with just 2, but the output is 1, 2.
It remembered the first call.
Why does it do that?
Because Python functions are not just blocks of code, they are actual objects stored in memory. When the Python interpreter reads that function definition for the very first time, it compiles it and stores those default arguments in a special attribute called defaults.
Ah, so that empty list is evaluated only once at definition time.
Exactly. It is not evaluated every time the function runs.
Our source used a great analogy for this. It's like a shared whiteboard in a conference room. You assume you're walking into a fresh, clean room for your meeting, but the first person who used the room wrote on the whiteboard, and when you walk in, all their previous notes are still there.
Yeah, and you just start writing over their notes. The fix for this is simple, though. You set the default to none, so container equals none.
And then inside the function.
No. Inside the function, you write an if statement. If container is none, container equals empty list. This forces the creation of a brand new list at execution time, giving you a clean whiteboard for every single function call.
That is such a good habit to build. Trap number 2 is operator mutation. The subtle difference between writing a plus equals a list with 4 in it versus writing a equals a plus a list with 4.
Visually, mathematically, they look absolutely identical.
Yeah, one just seems like a lazy shorthand for the other.
But to CPython's memory manager, they trigger entirely different mechanisms under the hood.
How so?
When you use the plus equals operator on a list, Python invokes a hidden method called iadd, which stands for in-place addition. It directly modifies the existing memory block.
Oh, so if there are other sticky notes, other variables pointing to that same list, they will all see the change.
Exactly. It's a silent mutation.
Yeah.
But when you write a equals a plus 4, Python invokes just the standard add method.
And what does that one do?
It is programmed to read the original list, read the new element, allocate a completely new block of memory, place a combined result there, and then reassign the sticky note A to this new block.
Leaving the original list totally untouched.
Right. It is perfectly safe.
This distinction becomes critical when we step into the tools used every single day in machine learning, like NumPy and data science frameworks.
Oh, absolutely. NumPy is where things get really wild.
Let's talk about the NumPy view trap. Say you have a NumPy array, just a simple 1, 2, 3. You slice the first 2 elements and assign them to a new variable called subset.
Okay, a standard slice.
Then you change the first element of subset to 999. Now, in standard Python lists, slicing creates a copy, so the original array is safe.
But in NumPy?
In NumPy, the original array actually changes. Its first element is now 999. Why does it do that?
Well, you have to think about what NumPy was built for. It's designed to handle gigabytes, sometimes terabytes of matrix data. To save RAM, slicing in NumPy does not return a copy, it returns a memory view.
A memory view, so it's looking at the same data?
Exactly. A NumPy array is really just a contiguous block of C memory. When you slice it, NumPy doesn't duplicate the data. It just creates a new metadata header that points to the exact same memory block. It just alters the strides, which are the instructions on how to step through that memory.
So modifying the slice actually modifies the underlying C memory block.
Yep, which modifies the original array. This is one of the most common ML bugs in existence.
And this brings us full circle to that 98% cross-validation disaster we started the whole deep dive with.
Yes, the in-place transformer failure.
We need to dissect exactly how an in-place mutation causes a model to look perfect in testing but fail so miserably in deployment.
Sure. So in cross-validation, you divide your dataset into multiple chunks, or folds. You train the model on 4 folds and test it on the 5th, and then you rotate.
Right, to see how it handles different data.
Exactly. Now suppose you write a transformation step that multiplies the first column of your matrix by 2, doing it in place with NumPy syntax.
So like x all rows column 0 equals x all rows column 0 times 2?
Yeah. During fold 1, the pipeline mutates the data in place. The model trains. Then the cross-validation loop moves to fold 2.
But the underlying data was never reset.
Nope. Fold 2 is now training on data that was already multiplied by 2 during fold 1.
Oh, wow. So fold 3 trains on data multiplied by 4.
And fold 4 trains on data multiplied by 8. The model is literally bleeding information across the fold.
This is massive data leakage.
Exactly. The model is learning artificial patterns. It's a hallucinated signal that only exists because the pipeline is repeatedly mutating the data. It memorizes this corrupted signal, which results in an artificially inflated 98% accuracy.
But then in production, data passes through the pipeline exactly once.
Right. The model encounters real data without those hallucinated compounded multipliers, and it just completely fails.
Drops to 62%.
Yep.
How do major machine learning frameworks handle this memory paradigm? Because we rely on these tools constantly.
Well, different frameworks adopt different philosophies based on their primary use case. Take scikit-learn, for
The
example.
classic.
Scikit-learn takes a very defensive approach. Its transformations generally return entirely new arrays by default. It intentionally avoids mutation to protect the user from exactly this kind of data leakage during cross-validation.
That's safe. But what about PyTorch? Because PyTorch is built for deep learning, right? Tensors and neural nets.
Right. And when you are training a massive neural network with billions of parameters, memory efficiency is critical. So PyTorch explicitly offers in-place operations to save memory.
How do you spot them?
They are usually denoted by an underscore, like add underscore with parentheses.
Okay, so PyTorch gives you the in-place option because you might actually need to mutate a tensor just to avoid an out-of-memory error.
Exactly. However, PyTorch relies on a computational graph to calculate gradients during the backward pass, the actual learning phase.
Right.
If you mutate a tensor in place, and PyTorch needs the original value of that tensor later to calculate the gradient, the entire training process will just crash with a runtime error.
Oh, so it stops you.
It does. The framework assumes the engineer understands the memory graph and the risks of mutation. It gives you the power, but it won't hold your hand.
So the tools give you the capability, but they rely on you, the engineer, to impose the safety constraints.
Exactly.
To build a bulletproof pipeline, professionals rely on a specific design pattern. Let's construct that pipeline architecture for the listener, step by step,
Okay. The first architectural layer is enforcing pure functions.
which means
A pure function reads the inputs and returns a brand new output object without modifying any external state whatsoever.
so in Python, that means ensuring we aren't using empty brackets or braces as default arguments. We use none and instantiate the objects inside the function to guarantee a clean state,
Yes, clean whiteboards every time. The second layer is the idempotency check.
testing the salt in the soup.
Exactly. Before a pre-processing step is merged into a production environment, it must be mathematically tested. If the function f is applied to dataset x, applying it twice, f of x must not distort the data further.
And if we are using NumPy, we implement explicit dot copy commands when slicing data that will be modified later.
Right, because we acknowledge that NumPy creates views by default. So we manually break that shared memory reference before applying any transformations.
And the final layer is pipeline safety validation. An engineer must be able to shut down the pipeline mid-execution and restart it from the very beginning without manually resetting the underlying database or clearing out mutated files.
If you can restart safely, your pipeline is idempotent.
We have a micro exercise from the deep dive sources to lock this concept in for you.
Highly recommend doing this.
Boot up a Python notebook, build a simple preprocessing function, pass some dummy data through it multiple times, and just observe the drift. Watch the values distort with each pass.
Yeah, once you actually see the mutation happening, isolate the transformation using deep copy and verify that the original data remains untouched.
And then, simulate a train test split. Introduce an intentional in-place mutation using NumPy syntax.
Watch how the data leakage creates that inflated accuracy score we talked about, and then refactor the system so it's idempotent.
Experiencing the bug firsthand really cements the necessity of the architectural fix.
It really does. Mutability is not just a quirky Python feature, it's a system-level risk. Uncontrolled side effects corrupt data, they generate deceptive metrics, and they cause production systems to fail.
It's the dividing line between writing experimental scripts and engineering reliable machine learning systems.
Absolutely.
If a subtle in-place addition operator or an empty list in a function definition can completely compromise a multi-million-dollar ML pipeline, bringing accuracy from 98% down to 62%, it forces you to question the foundations of your code.
It does.
What other seemingly innocent Python habits are silently corrupting your complex systems right now? It is something to seriously evaluate the next time you design a data workflow.
Really makes you think.
In our next lesson in the series, we are going to build directly on today's foundation. We will cover copying strategies and memory-safe system design, where we will learn how to design safe pipelines, control data flow, and eliminate shared state bugs completely. See you there.